Properties of continuous functions. If the functions f and g are continuous at x equal to c, then the following combinations are continuous at x equal to c. And look at this. This is very familiar. This is just the same as the properties of limits of a function, whether it exists or not. So if you have a sum, if I have two functions, okay, f and g, if f is continuous, g is continuous, that means their sum is continuous, their difference is continuous. Here, a constant times a function where the function is continuous makes constant multiples continuous. A product of two continuous functions are also continuous. A quotient of two continuous functions is also continuous, provided that we don't have a zero in the denominator. And a power of a function is also continuous, as well as the nth root of a function. Just to give you a few examples, if I have y equal to x squared plus 3x, this is a continuous function. Okay, it's powers of the identity function. Here it's a multiple, constant multiple of the identity function, and then the two together is the sum, and that makes it y equal to x squared plus 3x continuous. Okay, y is continuous everywhere. Okay, how about this one? Y is equal to sine x plus cosine x. Is that continuous everywhere? Okay, yes indeed, because sine x is continuous, cosine x is continuous, so their sum has to be continuous. So what are some common functions that are continuous? Okay, so far what we have been talking about are usually polynomials. Let's say y is equal to 3 x to the fourth plus 7x cubed minus 4x plus 7. Okay, that's a continuous function. Some trig functions are continuous. Some trigonometric functions are continuous. A few examples would be y is equal to sine of x, y is equal to cosine of x. What about y is equal to secant of x? Well, it will depend on the domain. So y equal to secant of x, cosine of x behaves this way: pi over 2, 3 pi over 2 up to 2 pi. Now if I take the reciprocal of when cosine of x is 0, then that's when it'll be undefined. So to graph secant, that's my secant of x. Well, it is conditional in the sense that it is continuous at certain intervals. Okay, so I will say it's continuous for all x not equal to any multiple of pi over 2 where n is an odd number, like pi over 2, 3 pi over 2, 5 pi over 2, minus pi over 2, etc. Other kinds of examples that I'm sure we'll be looking at is you will have the exponential functions and also the logarithmic functions. But we have to be careful about our log functions. We say it's continuous in its domain, okay? Because if I draw the graph of a log function, the domain is going to be from 0 to plus infinity. So as long as we're in this interior, the function is continuous. This is just a few of our common functions that are continuous. How about if we have a composition of functions? Well, what this diagram shows that if I have a continuous function f at c, so then that means it will have an f of c, that's the limit as x approaches c. And then I'll have another continuous function g, which is continuous at f of c. Then my composition will also be continuous. That's all that this is saying. Example, suppose f of x is sine of x. How do I know that g of x is the absolute value of x. Both of these are continuous, right? Okay. Remember that the graph, let's look at the graph of sine of x. Well, we just did it a while ago. And then the absolute value. And remember that it continues on. If I have g of f, what does that look like? I'm taking the absolute value of sine of x. Is this continuous? Question, is that continuous? Well, based on this diagram that I have here, that if I have a composition of two continuous functions, then the composition is also continuous. Even if I don't have to graph that, I know that the sine of x, the absolute value of sine of x is continuous. Well, I could graph it. What do you mean by the sine of absolute value of the sine of x? Well, here's my sine of x. Wherever it's negative, you just make it positive. So what you're actually going to see is right there. It's like a scallop. And so on and so forth. Okay. There you go. And notice there's no gap, there's no hole, there's no jump. And so we have that the absolute value of sine of x is continuous. Here is another example of a composition function, but just to show that the function y equal to, let me write that down. It's like this. Ooh, I need a red color to be more visible. Just to see how it looks like. Y is equal to the absolute value of x sine of x over x squared plus 2. Do we have any problem as far as having a 0 in the denominator? No, because x squared plus 2 will always be positive and non-zero. At the top, you have a continuous function times the identity function. They're continuous, okay? So the ratio of two continuous functions, as long as there's no 0 in the denominator, okay, that is continuous. And if you take the absolute value, then it's also continuous because the absolute value function is continuous. Let's go back to situations where there is a discontinuity at a point. Well, let's go ahead and examine A and compare it with B. Okay, this is a very familiar function. You've seen this before. That's y is equal to sine x over x. Okay, and what did we say is the limit? Well, you can look at it graphically. That the limit, I'm going to A. We are looking at A, and let's go to our checklist. First of all, what is f of 0? F of 0? Well, what's f of 0? Uh-oh, it does not exist. Number 2, what is the limit of f of x as x approaches 0? Okay, as x approaches 0, coming from the left and coming from the right. Where do our y values approach? Ta-na-na-na-na-na, I'm going to 1 from the left and from the right. So the limit is 1. Question, do we have to continue to say to decide whether it's continuous or not? Of course not, because this is not met. The first condition is not met in our continuity test. What can we conclude? It is not continuous. Not continuous at x equal to 0. Okay, let us compare it with B. Here, B is a redefined function of f. And let's just look at it like this way. Let me redefine f of x to be sine of x over x as long as x is not equal to 0 and it's equal to 1 for x equal to 0. Okay, well, let's look at our checklist. first, what is f? Capital F of 0? It's 1. Check. Number 2, what is the limit of f as x approaches 0? Yay, it's also 1. And because of this matching together, okay, 1, or rather f of 0, okay, that's condition 3, is equal to the limit of f as x approaches 0, and that's equal to 1. So continuity test, number 1 met, number 2 met, number 3 met. Yay, we're good. Basically what we did in between A and B is that B is when the discontinuity of A has been removed. Okay? So whenever we have a removable discontinuity, that is when the limit exists, but the function value at that point does not exist, and we remedy the situation. That's why it's removable. We remove the discontinuity by plugging the hole right there. So we can remove the discontinuity from the graph by defining a new function, and there's your new function. Okay, it's equal to sine x over x everywhere else except at x equal to 0, and we plug a hole by defining f of x equal to 1 at x equal to 0, whenever x is equal to 0. This is what we call a removable discontinuity. Oh, here is another example of a removable discontinuity. Let's look at letter A and rewrite y in terms of its factored form, x squared minus 4. Let's rewrite, and we have that this will be x plus 3 times x minus 2 over, factor the bottom, that's a difference between squares, x plus 2 times x minus 2. Question: what is the limit of y as x approaches? What will make this 0 at the bottom and on the top? It's when x approaches 2. The limit is equal to, the limit is equal to, well, I can go ahead and cancel as long as x is not equal to 2, and it'll be 2 plus 3 over 2 plus 2. That gives me 5 over 4. Question: what is y of 2 though? If I plug in x equals 2 on this function, I am in trouble because it'll be a 0 over 0, so it's undefined, which means it does not exist. So we have a point of discontinuity at x equal to 2. Is it a removable discontinuity? Yes, because the limit exists, it's just that it has no function value at the point x equal to 2. And so we remedy the situation by letter B. So to remove the discontinuity of A, we redefine it to be, okay, a new function. And what is the new function? It's really what's left over when we canceled x minus 2, both the top and bottom. So in B, our y is equal to x plus 3 over x plus 2. Is it continuous at x equal to 2? Let's check. What is y of 2? Well, that's what we got there. It's 5 over 4. Number 2, what is the limit of y as x approaches 2? It's right there. It's also 5 over 4, which makes number 3 that the limit of y as x approaches 2 You should put 2 right there. 2. Okay. Is our function value y of 2, which is 5/4. So condition 1 is met, condition 2, and both of these is just to conclude, which is number 3, that they're equal, therefore it is continuous. Yes, it's continuous. Okay, so we're saying that B is the continuous extension of A. Okay, because we have removed the discontinuity here at x equal to 2. Yay! To recap, what did we look at? Different discontinuities, and where have we decided that it's removable? Okay, well, letter A, we know that this is the only function that's continuous. Here, it's not continuous because it's not defined there. Here it's not continuous because they don't even match. Here it's not continuous because we have a jump. Here it's not continuous because the limit does not exist. So both D, E, and F, all of this, the limit does not exist. So limit does not exist. Limit as x approaches 0 of F. Again, here it does not exist. Same thing here. The limit of F as x approaches 0 does not exist. Okay, so between D, E, and F, we do not have a removable discontinuity. Between D, E, and F. But at B and C, these are what we call removable discontinuity. Okay? Both of these are removable. But for D, E, and F, because the limit does not exist at the point x equal to 0, or for arbitrarily x equal to c, okay, the limit does not exist, then we don't even consider it at all a removable discontinuity. So we can only remove the discontinuity if the limit exists. Okay, we will stop right here, and then I will continue with working out problems from the back of your book. From at the end of section 2.5. Okay, stop. See you next time. Bye.